Alright, hello, my name is Miguel. I'm a student at Ozbay's class for fluid dynamics, and this is my first project. So right now we're gonna do a Couette and Poiseuille flow, and we're also gonna do a hybrid of both in our simulation. For starting the simulation here, I'm gonna be using Ansys Fluent. I find that the fastest way of doing the simulation is instead of just doing multiple fluent flows like this for each case, instead what we could do is delete these instead and go through not geometry but mesh right here. So that way, once I get the mesh done, I could share that mesh with 3 cases instead of having to do a mesh for each and every time, which would be very inefficient. Just go to here, and here. There you go. So you see it's shared. So once I have my geometry and mesh done, it'll be shared for all the cases here. I'm going to name this one case C, and we can rename this one case B, and rename this one case A. Alright, first let's start with the geometry here. Go here. I use discovery. This is new to me. I'm still kind of learning all this, but I've been becoming more of a fan of discovery, so that's what I'm going to use. It'd be best if we close everything in the background so everything goes quicker. There you go. Alright, we're in discovery. Go to model, and here's where I'm gonna be doing my actual modeling. Go to sketch. I can press V to be in the normal view plane. Now we're gonna be drawing our domain here, fluid domain. So I'm gonna make a rectangle. And in the assignment, the length of the domain has to be 150 times the height. So in here, I'm going to be going like this. There we go. In here, we're going to be going 0.01 meters, 10 millimeters. Alright. Then in here, we're going to be going 1.5 meters. So 10 millimeters times 150 will give me 1.5 meters. That's pretty much it. We're done here. Well, not really. Actually, we gotta name our walls. So I'm gonna go here, click on the wall I want, Control G, and then name this inlet. And click on this, Control G, outlet. This, Control G. This is gonna be upper wall. Click on this, Control G, lower wall. And done. pretty much it. Now I gotta leave the sketch, so you can press D or 3D mode right here. And we've already made a surface. That's good. That's exactly what I want. Go. And that should be it. Now we could close the assignment and close the geometry. Now we go to mesh. Go. Gotta give it a minute. Alright, we have all our boundaries here, well, named selections. They're pretty much our boundaries, just good. Always make sure it's correct. And now, here. Now, before I mesh, what we're going to do is default element size. I'm going to try setting that to 0.005. Go. And then we're going to go here to sizing. Insert sizing. Geometry, I'm going to select bottom and top. Now, if you see in my mouse cursor the little weird mouse cursor glitch, that's because Ansys does that if your graphics cards are not up to date with drivers and everything. However, I just updated my drivers yesterday, and it still does it. You're just gonna have to deal with this annoying thing. Sorry about that. Now, we selected both the edges, so and now in here, instead of element size, I'm gonna go number of divisions. And for number of divisions, since I have the full license and my laptop's actually pretty nice, I'm gonna try going up to 4,500. You might have to lower it depending on your computer power, but 45 gives me a nice quality mesh. Here I'm gonna also go to sizing, and now I'm gonna select my inlet and outlet. Go. Change element size to number of divisions, and we're gonna go with 200. And now we should probably rename these just in case we want to edit it back later on. So I'm gonna name this inlet, outlet, and then this I'm gonna rename walls. There you go. Now, for the walls, I'm going to set the behavior to hard here. And then for inlet and outlet, I'm going to change the behavior. Well, the behavior stays soft. And the bias, we're going to add a bias here. You could kind of see how the biases will look like here. We're going to select this one, the third one on the bottom. What this will do is set the bias so the edges of the walls are more finer than the middle. This will kind of help get that boundary layer much more accurately without really putting too much computational power and too fine of a mesh in areas you don't really want. Bias factor, I find 2 work pretty nice for me. So and then I'm going to add another one. This time I'm going to be doing face meshing here, and face meshing we just click on the surface, apply. There you go, and quadrilaterals, that's nice. And now we mesh. This might take a while, so yeah. Alright, the meshing is done. That was actually pretty quick. Now we could check our mesh right here. This looks very nice. You can see the bias does. The center here is a little bit more coarse. Oh my gosh, this smells. The center here is a little bit more coarser than the edges right here. You want more focus near the edges, near that, closer to that boundary layer, because that boundary layer is kind of, that's where you get all your drag forces and all your forces and all that. Although this time we're not going to really be focusing on our forces. And it still is pretty nice to focus more on the boundary layer. It's just great practice. So yeah, that's pretty much done. Our name selections is still there, good. And now we could just close the mesh. There we go, and then click update. Alright, it's all updated. This is the great thing about having a mesh shared. You don't have to redo it. You don't have to redo it ever, because it's just shared. So everything already has it. All I have to do is just change the setup for each and different case, which regardless I'll have to. So here, I'm going to click edit. Open up our Fluent. It already sees it's a 2D dimension. It's great. We're going to go to, I'll go 6 cores because on my laptop I have 6 performance cores, and I'll click double precision. Okay, there you go. Now you can see the warning we have here. I'll fix it when we get there. You're gonna see what it is in a minute. So yeah. Now our simulation, keep these just pressure base, absolute, and steady. There you go. And the model, we're instead of K omega, we're gonna go laminar because that's what the assignment asked for. We know we're gonna go laminar because our Reynolds number would be, it would be less than, what was it, 2700. So that's why, we're gonna assume laminar condition here. Materials, I'm gonna check here. Air, I'm gonna leave the air as normal like this. This is just a default air that we typically use. Now our velocity would depend on our viscosity and density, and that's because we're trying to aim for a target Reynolds number. And if you know, the Reynolds number would equal your density times velocity times x, or L, which is your length, divided by your viscosity. So We're going to leave these the same here. And now here we're going to go down. Cell conditions. The error here is saying our flow boundary outlet is adjacent to a solid zone. This problem must be fixed before we can proceed. And that's because it assumed that the surface was a solid. I'm going to have to double click cell zone. Typically, Ansys wouldn't really make this mistake. It would kind of already assume a fluid. But every now and then it will do this, so you gotta always double check. So yeah, there you go. This apply is okay. And bam. And there you go. Now I'm gonna remove these errors. Close it. There you go. So now it knows that it's a fluid and that it's air. Our boundary condition, we're gonna be doing the Poiseuille flow first. So we're gonna change our inlet velocity to what we calculate. So let me get some numbers here. Okay, so our velocity, if we want a target of for air, we would want a target Reynolds number of 250. Well, you could use any target you want, but I find that with air, a Reynolds number of 250 would be best for your Couette flow. And even though we're doing Poiseuille, I want to keep my Reynolds number consistent with all different cases. So we're going to be doing with the Reynolds number of 250. So with the Reynolds number of 250 and our conditions of viscosity and density that we have from air that Ansys already gives us, we will get a velocity of 0.3651837. That's a lot of decimal points, but it's good. And there you go. Also, I just realized when I explained the Reynolds number formula, I was correct. No. When I explained the Reynolds number formula, I was actually wrong. It was actually density times velocity times diameter, or my height in this case, which is 10 millimeters, divided by my viscosity. So, yeah. Alright. Now, interior, internal, that's alright. Outlet, just check that the pressure is just 0. Just our gauge pressure is 0. It's okay. And then our walls, check that they're no slip and they're just stationary in this case. There you go. Yeah, see, stationary, no slip. That's good. Alright, and then that's pretty much it. Now we could go down. And then residual, I want to change this since I am pretty confident in my mesh. I'm going to go 1e to the -8, which might be excessive, So actually, I'm going to try going to -6. No, let's go -8. Why not? 1e to -8 is pretty excessive, but I have all the time in the world, so yeah. Alright, let's go -6 just so we save time. I may have all the time in the world, but I'm not going to wait that long. Alright, so there you go. If you're wondering what this does, your absolute criteria, this is when it will determine to stop the simulation once it sees convergence. So if your residuals, if these parameters here reach a value under 1e to the -6 on all three of these, then it will say, hey, we see convergence here, so it will just stop this simulation there because there's no point in continuing if you already see that your parameter is already converged. So there we go. Now that that's done, we can go here to initialization. and we could click initialize, or we could probably look in, let's go standard initialization. We're going to compute from the inlet, and our x velocity will be, yeah, right here, the value that we calculated. Now we initialize. No, instead we're going to be doing hybrid initialize. There we go. Yep. And there you go. Done. I'm still learning the differences between initializations here. I always pretty much use hybrid, but recently I've been learning standard, so that's why I kind of went with it. But I'm going to keep it like that. Why not? And then now we could run our simulation. I'm just going to put 1000, though pretty much it's going to stop way before that because of the, we changed the absolute criteria of our residuals. So there you go. And click calculate. There you go. And you're going to have to wait for a bit. Alright, and it's done. Press OK. And yeah, you can see here in our residuals, once everything reached the value at or under 1e to the negative 6, it will just stop. So even though I put 1000 a number of iterations, it stopped just before 40 because you already saw that it converged. There you go. So we're done here. We can close the simulation. Done. And now we move on to results. Okay. Now we're in the results page right here. Well, application. So first thing I'm going to do is create lines in the middle, at the end, and one close to the inlet, so we can see our velocity profiles. Click here, line, and I'll name this. And keep in mind where your model is according to your reference frame. Your coordinate system. So this is x, y, and z. And our x, we're going to go 0.75. And then we're going to keep this one 0.75. And this one will be 0.01. you go. And samples, you can put 200, whatever. And there you go. And then we repeat the same for the different locations that we want to record our velocity profile. It's 0.2, 1.4, 9. Now we didn't go 1.5 exactly, because if we go 1.5 exactly, you just can't get a result at the very end, so you gotta go a little before it. So go 0.01 and apply. There you go. You can see it right there. And then create a new one. 0.1. Let's go like 10 millimeters from the inlet, and then 0.1. 200. Yeah, looks good. And then now we're going to create contour of our velocity. So you're going to do U velocity right there. Location, we'll go symmetry 1. Domains, yep. Variable, we're not going to do pressure, we're going to go velocity U. Velocity U is a velocity in the x direction. Velocity V is velocity in the y direction. Velocity W is velocity in the z direction. So we're going to choose U because we're looking at it from the x direction here. There you go. Range, click global. Contours, let's go 15. Click apply. And there you go. So I could zoom in real quick, and you can see velocity contours. Yeah. Yeah. Now I don't like how the legend, I believe it's called, like where you can see the legend here, it's just in the way. So we could change the location of that. Just double click on this. Or heck, you could right click and edit in command editor. And well, not yet actually. So go here, click horizontal, and I just click none and none. There you go. So you can see it's in the bottom here, just much nicer. However, I do want to get the smaller letters here, and I don't want this exponent here. I want to just consistent numbers. So what we can do here is just click right click, edit in command editor. Now open up all of this. Shorten the size, so let's go 0.5. Format, click F, and then text height, let's go 18. Process, and there you go. See how much cleaner that is? It's much better. There you go. And there you go. Zoom in a little bit, and that's pretty much it. There you go. Now we gotta create charts for our velocity profiles. So chart, and my name is whatever, something like that. Velocity profile, there it is. Then now in our x direction, we're going to set that as velocity u. In our y direction, this would just be y, the y location. There you go. Now we go to data series, so we tell what data to collect. So this one we're going to go point region. The location, this will be on the M line, which is what I named here. Click apply, and you can see it. You can see the velocity contour right here. velocity profile. I mean, right click new and do the same for the other locations. And there we go. The midpoint region is basically the same as the outlet region because it's already fully developed. So there we go. If we want, we could also just move this more to the back if you want to see how it changes. So I could go here. Instead of 0.75, let's go like 0.5, 0.5, apply. It's still fully developed. Let's go 0.25, 0.25. Still very developed. 0.1, 0.1. And there you go. Now you can see it kind of developing there. So I'm going to leave it how it was though. So, yeah. Yep. And that's pretty much it. We could also do streamlines, but it's just a laminar flow just going straight, so there really isn't a point of it. But yeah, there you go. Oh yeah, we could also do, let's do a vector plot. Why not? Vector. All domains, location, symmetry 1. 6. This is my first time using this, so I might get this wrong here, but oh, there you go. Okay, so let's hide the contour region. And yeah, now you can see how the vectors kind of move. The vector is a little bit too big, so we're going to change the factor. Wait, maybe it's not factor, it's edit. Okay, well, whatever. I haven't really played with this as often, so I can't really say. Yeah. There you go. So yeah, they're all just going straight. This isn't really a nice vector field, but it's alright. Synthesize. There you go. There you go. I can make it much nicer. Yeah. Instead of equally spaced, just go. No, random. There you go. It goes. Probably go 1,000. There you go. Yep, you can see how the focus of the velocity vectors. Let's go even more. 2,000. There you go, that's much better. And instead of line arrow, we could do is I should like that one. I don't think I'm a fan of these ones. Oh, there you go. But there you go. That's much nicer. So yeah, you can see the velocity vectors is just basically going along the path, and the velocities closer to the wall, those are pretty slow. That's a boundary layer forming. So yeah, that's done with. We're done with the Poiseuille flow. Let's go to the Couette flow. Here, 6 because that's 6 performance scores, dope precision, and yep. Alright. Same errors. This is going to be the same thing in the other case as well, so let's just clear this. And now for the Couette flow, we don't want a velocity inlet. Instead, what we'll do is make it a pressure inlet. And boundary conditions. There you go. Inlet, pressure inlet, and there you go. Just set the pressure to 0. And our velocity this time will be from the moving wall. So we're gonna have the upper wall be moving. So double click on this guy right here. And we're gonna set this one as moving. Translational. Direction will be, this is the direction here, just set as 1. And the speed would be the same as what we got before. 6, 5. Go, apply, and yeah, that's pretty much it. You can also check the other conditions, but they're the same. Like if you check outlet, gauge pressure should be 0. Yep, there you go. Let's go back here, monitors, and 20 -6. Now, this simulation will take longer to run, simply because we have a moving wall in here, and that will just add more complexity to the simulation. So I expect this simulation to take quite a while. So instead of 40 iterations, as we saw were converged, this one might go over 100. So let's see. Initialize. And yeah, you can see that the initialization is taking a little bit longer, and that's because the simulation here is just a little bit more complex. So, yeah. Alright, and we are done. As you can see, it did take much longer. Had my Y velocity residual was rising for a little bit. But at the end, everything just drops down and converged. So it's nice. Yeah, heck, we could also view our results here in the results tab in Fluent, but I'll just be doing it in the other program. So there you go. Alright, and now we're gonna repeat basically the same exact thing as we did on the Poiseuille flow for viewing our results. Create our lines. Create another one. Alright, and there you go. Now, as expected with the Couette flow, we got a linear profile once it's developed. So, yep. And when it is developing, you'll get this velocity profile, and as you move along, it kind of becomes more linear as it becomes, and then it becomes like this. So, yep, it's good. Which this the Couette flow is the reason why I chose the Reynolds number of 250. If you were to choose a higher Reynolds number, like let's say 200, even though it is laminar, you will get a graph that will look something like this, kind of like how my mouse is moving, it will go steeper, and then later it will become less steep like this. So yeah, but it's fine. There you go. And I could also make me my vector velocities. It was this one. Yep, you can see it kind of linearly progressing. So that's to be expected. And yeah, there we go. Now let's move on to the final case. It'll be basically the same thing. However, this time we're going to be combining both of them. So there you go. Oh, there you go. Okay, there you go. Yeah, sometimes my Ansys is it'll do that sometimes. I just gotta wait for a bit. All right. Alright, now this is where the differences will come up. So velocity magnitude will be basically the same as the Poiseuille flow. 2, 6, 5, 1, 8, 2, 7. There you go. And then the walls would also be the same. Upper wall. And we're going to do the same as the Couette flow. Moving, same direction, 0.35, 365, 1837. There you go, press apply. There you go. So this time now we have the velocity inlet and the moving wall kind of moving the flow. So there we go. And Yep, there you go. And there you go. Now, if I remember correctly, when I first did this, the hybrid was actually, I believe it ran quicker than the Couette flow. And I'm guessing it's because the pressure inlet was 0, so that's why it was just, taking longer, if I remember correctly. But yeah, we'll see. Yep, there you go. Yeah, this one ran quicker, so could close it. And move on to results. And this is basically the same thing as we did before. Well, not basically, it is the same thing we did before. This is go. Oh yeah. I'd actually like a better color for this. So if you want to change the color, I recommend this one. There you go. Yeah. So you don't get all that bright green. Or you can change the color too if you want. I'm gonna do it for this one because I feel like it. So yeah. Go horizontal. I'm just go none, and then apply, and I could probably change the parameters in here also. Yep, there you go. Looks nice. No, this one. Yeah, and yep, that's pretty much expected. Just like that. And yeah, I'm pretty sure, yep, that's it. So we got our contours, velocity vector, and we also have the lines here. Heck, if you want, you could also do streamlines right here if you want, but that's pretty much it for today. So yeah, that's pretty much the project already finished here.